Hello, my name is Jason Schoeters and I'm here today to present to you VectorTSP. This is a work I recently finished with my PhD advisor, Arnaud Castet, and with Mathieu Raffinot. So the whole aim of this work was in some sense to add some kind of acceleration or speed or inertia forces to the TSP. We'll go over some of the most well-known versions of TSP and explain why they are not very well adapted for this. So probably the most well-known version of TSP is the Euclidean TSP, in which you are given n cities to visit in the plane, and you want to visit these cities with a tour as short as possible and go back to your starting point. And so a negative point of this, if you want to add acceleration, is that Euclidean TSP is evaluated by distance in between the points in the plane. And so maybe you do not want to evaluate by distance if you want to add, if you have a vehicle that can accelerate. You might want to evaluate by time needed to cross the distance. Also, you allow for sharp angles in the Euclidean TSP, which might not be a very good idea if you have a vehicle such as an airplane which cannot make sharp turns like this. An improvement on this is the Dobbins TSP, because as we will see, even though it's still evaluated by distance, a tour is still evaluated by distance, you do not allow any sharp angles in the Dobbins TSP because the Dobbins vehicle can only turn on the outside of a circle of a certain given radius. It cannot turn any tighter than that. And so what we do in this work here is we actually add some way to represent acceleration in the TSP, in which we add racetrack constraints. And so racetrack constraints are the following. I'm not going to give you a bunch of definitions. I'm actually going to show you the game from which the racetrack constraints come from. So the game is simple. You take some math paper, so paper with a grid on it, and you draw some boundaries and some racetrack on which you have a starting region and a finish region. And you have to go around the track. So each round, because the game is played in rounds, you get 9 options to choose from to where to go on your next round, as you can see here. And you might wonder, well, how do you define the following 9 options? Well, it's actually really simple. You take your last position, which is over here for me, and your current position, which is over here for me, and you consider the vector that is between these two positions, and you translate it onto my current position, which actually leads me to the middle of my 9 possible choices. So I choose one, I translate this vector, which leads me to the middle of my 9 points, and I choose again, and so on. And so what is really well done with these racetrack constraints is that you might not see it before it's too late, that you are going too fast and you might crash into a wall. For example, here, I think I might be going too fast. We will check. So here we already went pretty fast, but I will not crash into a wall the next round, but I'm afraid I might go into the wall in 2 rounds. Yeah. So here I indeed crashed into a wall. So it's not too obvious if you will crash into a wall in a few rounds or not. So that's really what the game is about. So let's go back to my slides here. So it has a lot of names. We will just stick with racetrack, but another popular name is vector racer. Considering its origins, well, it's come from all around the world independently, apparently. It's such a simple and intuitive game, but people often cite Martin Gardner because he took the effort in 1973 to properly define and present the game. So now what happens if you take these racetrack constraints and you put it into a TSP, say in an Euclidean TSP. So give an instance of n cities in the plane with a starting city P0 and an integer k, you might ask the question, does there exist a racetrack trajectory? So a trajectory as I just drew in the plane, in the game, sorry. that respects the racetrack constraints of a length at most k, visiting all cities, starting and finishing at p0. And of course, you can define the optimization version in a similar fashion. And just as a remark, well, these problems defined like this, they're artificially hard in the sense that verifying a solution takes exponential time. So to avoid this artificial hardness, we decided to add a padding parameter, which we call L, which is going to represent the largest distance between any pair of cities given in unary. And so this L is given as well in the input or the instance of the problem. So I'll give you a quick example of what such an instance might look like. So this is something we coded. So this is an instance with the P0 in the middle and other cities to visit all around. And a solution might look like this. So it's a line of alternating red and blue, which is to show different vectors that are right next to each other. And so at the end, we see that this trajectory in red and blue takes 86 vectors. So in the optimization version, you might want to optimize this 86 to try to go down. For example, here, this might not be very optimal, but maybe it is, I'm not sure. So that's just to give an example of an instance and a possible solution, maybe not the optimal one. So let's go on. So in terms of variations of the VectorTSP, and also in terms of different parameters you can give, of course you have the dimensions. So we consider in this presentation 2 dimensions. You can consider a maximum visiting speed, which is gonna say, which is gonna be allowing at what maximum speed you can traverse a city and consider it visited. So for example, we consider any speed that traverses a city to visit the city. But if you put this to 0, then that might represent like trains or buses that have to stop to pick up passengers and to drop them off somewhere else. They have to stop to do that. They do not go through at a certain speed. So you can also consider a maximum visiting distance. So this is very similar to the TSP with neighborhood. So instead of just visiting the exact location of the city, you might want to consider a radius around the city. And if you visit inside the radius, and you consider the city to be visited. So by default, we do not consider this. And you might also consider a parameter, which is a bit special, which is called the vector completion parameter. So it's a Boolean parameter, which we consider by default to be false. And so this is going to define whether you consider a city to be visited if it's visited between rounds. So in some sense, this might represent sensors that only sense or only activate every couple of maybe milliseconds, I don't know. And so last but not least, you might consider other successor functions. For example, we considered as a default successor function, the racetrack successor function, which is to the left here, which I presented in the game. But you can also consider maybe only 5 successors instead of the usual 9 in racetrack. Or you might want to add to these successors, so maybe 13 or 21 successors. Or on the other hand, you might want to consider a continuous space of kind of successor function, such as shown here on the right. And so these parameters all serve to maybe solve ambiguous cases of whether a city is visited or not. For example, this one, is this city visited or not? Well, only if vector completion is set to false, because this drone is obviously between rounds, between vectors. And only if maximum visiting distance is at least 2, because they're a distance 2, the drone and the city. And only if maximum visiting speed is at least 7, because this vector on which the drone is at least is of size 7. So let's go on with some minor results, I would say, from our paper. Maybe you might say some insights. So the first one is that an optimal Euclidean TSP visit order, if you can compute it, which is already hard, of course, may not be optimal, in fact, for the VectorTSP problem. So what this means is that if you visit a given point set according to the Euclidean TSP visit order, the optimal one, such as shown on the left, and you try to do you do this optimally with the number of vectors, the minimum number of vectors, you might still use more vectors than the real optimal solution for VectorTSP, which is shown here on the right. So this is just an example, but there's many more cases in which this can actually happen. And so yeah, on the right, you use two less vectors than on the left here. And so you might say, well, what if you consider a maximum visiting speed of 0, which you talked about earlier? Well, yes, if you consider a maximum visiting speed of 0, then this is not a good example, but this one is. So this one, the optimal Euclidean TSP visit order is obviously the convex hull in some sense. So you go from here to up, to the right, to below, and to the left again. But we found out that the VectorTSP optimal visit order is actually the other one. So it's this one, go to top, and instead of going to the right, you go below, to the right, and you go back. And a nice corollary of this fact is that an optimal VectorTSP trajectory may in fact self-intersect and still be optimal, such as the one on the right here, which is of course in contradiction to the Euclidean TSP, which cannot intersect or it's not optimal due to the triangle inequality. So for the following lemma, we need to define what a phase space is. So a phase space can be seen as a directed graph in which the nodes or the vertices represent configurations of which are of the form of a tuplet like this. So x, y, dx, dy, which are going to represent the position of a visiting vehicle as well as its speed. So think of it as all possible states in which a visiting vehicle can be, okay? And so these configurations are actually connected to its successors by arcs. And so as we have seen before, you have 9 choices at every round. So you have 9 successors to which you connect by arcs. So our little lemma here says that the phase space for a given VectorTSP instance is in fact polynomially bounded. And here's the proof ID. So you take a simple solution, and here the simple solution for us is the bounding box walk. So the bounding box walk is when you have all of your points in the plane here, you take a bounding box surrounding all of these points, enclosing them as tight as possible, of course. And then you walk inside this bounding box at minimum speed, so at speed 1, or even you can even consider speed 1, stop, speed 1, stop, speed 1, stop. And you go one by one, row by row, or line by line. You go over this bounding box, and then you go back to the start. So this is a simple solution because you visit every city because they're inside the bounding box, and you visit everything in the bounding box. And it's of size L to the D vectors. Now that means that the optimal solution is also bounded by L to the D vectors. And this in turn means that the speed components are bounded by L to the D as well, because you can only accelerate by 1 every round. Okay, and in turn you can compute the position components as well, which are bounded by L to the 2D. And then if you multiply them all together, you get a phase space which is polynomially bounded by big O of L to the 6D vectors, or nodes rather, sorry. So let's go on with some complexity results. So our first complexity result is actually a reduction from VTSP to group TSP. So group TSP is the following. It's like a TSP, but now you have groups of cities. So not only cities, but groups of cities. And you want to visit each group at least once, not every city, each group of cities at least once. So how do we show this, that VTSP polynomial reduces to group TSP? Well, we use the lemma that we just proved, considering the phase space. And we go over the phase space, which is, of course, polynomially bounded. And we check for every node, every configuration in this phase space, if it visits some city. If it visits a city PI, then we group it together with all the other configurations that visit PI. And we do this for every city PI. Afterwards, we put arcs between every group. So not inside the groups. We don't put arcs inside the groups. We only put arcs between all members of distinct groups. And then on each arc, we put the cost of a shortest path. And shortest paths, of course, in the phase space, you can compute them polynomially. And in the end, you remove all the other configurations who do not serve anymore, and you end up with a group TSP instance. So as multiple corollaries, we have that vector TSP not only reduces to group TSP, but also to asymmetric TSP, because group TSP reduces to asymmetric TSP, and asymmetric TSP reduces to symmetric TSP. So VTSP reduces to all of these as well. Now, next complexity result is a bit more complicated, and I will not go over the details, but I will give you some general intuition, I suppose. So we showed that vector TSP is NP hard as well, and so that it's NP complete. And we did this by Papadimitriou's method. So in which in 77, he proved that the Euclidean TSP is NP complete. And so he did this by taking an NP complete problem, of course, and reducing it to Euclidean TSP. So the problem he considered was exact cover. So exact cover is you have some universe of elements, and you have some subsets of this universe. And so the question is, does there exist a combination of these subsets that cover each element in the universe exactly once? And so here is the proof. So it's quite complicated, and I will definitely not go over it completely because I simply don't have the time. But if you want to take away at least one intuition, then it might be this one. So look at the C1, C2, C3, C4, etc., up to Cn. These represent in some way the n subsets of exact cover. And this is the VTSP instance, by the way, this image, because we use a lot of gadgets. But so every CI gadget represents a subset from exact cover. And if in the optimal VTSP solution, you traverse C1 in one of the two ways, then the corresponding subset is included in the solution. However, if you traverse C1 in one of the other ways, so there's only two ways to traverse C1, then the corresponding subset is not included in the solution. So that's the only intuition that I'm going to give here, but it's really missing a lot of information, but I don't have the time. So let's continue. So we did the complexity part. So now let's look at algorithmics. So a basic idea of everyone, I suppose, is to, when you look at some new problem, maybe you want to see if existing algorithms already solve this problem or might be adapted to solve this problem. But we had a problem with this because we don't have any fixed edge costs between cities, such as any other TSP has as an input. And we can't really compute them as well because it's not really clear if you should compute them from 0 speed to 0 speed, or should you assume that they come in at this angle or this angle with this speed or this speed. It's really not that clear. And so maybe you can reduce it to group TSP and then look at the group TSP algorithms, but to the best of our knowledge, the group TSP algorithms are not very interesting, especially not if it's not if it's not a symmetric instance. Anyways, so we couldn't really take any TSP algorithm. So we found a solution in which we considered a TSP algorithm which doesn't really depend on edge costs, but instead depends on visit order completely. And this is the two-opt, or the flip algorithm, also known as. So this algorithm is great for us because for one, it doesn't use edge cost, or at least you can make it so it doesn't really depend on edge cost. And it also tests visit orders that potentially self-intersect, which is great for us because we have shown that self-intersection might be really good for our VectorTSP. It might even be optimal. So how do you adapt the two-opt for VectorTSP? Well, first of all, you need some oracle, which we're going to discuss afterwards. An oracle which takes as an input a visit order and which outputs some cost corresponding to the visit order. What you do then is you test permutations of some given initial visit order. And let's suppose this given initial visit order is our bounding box walk from before. So a really simple solution, which is of size L to the D vectors. Now, you test permutations of this initial visit order, and whenever you find something better, you test permutations of the better one, and then you find something better as well, and you go on like this until you find no better permutation. Then you stop and you return the result, and this result is known as a two-optimal visit order, which is not to be confused with a two-approximation. So this runs in time big O of L to the D n squared times the complexity of the oracle. So let's look at the oracle. How do we make an oracle that takes as an input a visit order and outputs an optimal cost corresponding to this visit order? Well, at first we thought of a BFS through the phase space, but we actually found a way to use the A star algorithm, which is much faster. So what the A star does, it's guided by some heuristic. And so by being guided, it goes around until it finds the optimal solution in some sense. So this guiding heuristic is very interesting, but I don't have the time to explain it either. But it's based on a one-dimensional version of our instance that we take. So we kind of take the shadow of our two-dimensional instance. We look at it from on the y-axis. We look at it from the x-axis, and then we compare these two, and somehow the minimum guides our A star algorithm. So this actually runs in time big O of n times size of the phase space. So the size of the phase space, we already said, it's L to the power 6D. Okay, I have to go a bit faster here. So when you plug this in into the two-opt, you get a polynomial time algorithm, if you assume D to be fixed, the number of dimensions, that computes a two-optimal visit order. So for the experiments, we had two aims, two goals in some sense. We wanted, of course, to validate the two-opt that we just presented for the VectorTSP. And we also wanted to, maybe this is the most important experimental aim, we wanted to motivate the VectorTSP as an independent problem, especially from Euclidean TSP. We wanted to see if an optimal solution for Euclidean TSP, is it actually a really good solution for the VectorTSP, even though we've shown that sometimes it's not optimal? Well, that's what we did. So we used Concord, which is a TSP solver, which gave us a lot of optimal visit orders for instances, for which we computed an optimal racetrack trajectory, and we put our two-opt against it. And so what you can read from these graphs here, I don't really have much time, so I will go only over the blue results here. So the blue results are the percentage of instances tested which admit at least one flip. And so we did a number of experiments. First one was we upped the number of cities, so we made the number of cities vary. You can see that the more you have cities, the higher the ratio of VTSP, 2-opt admitting at least one flip. So this one doesn't really admit any, there's no real correlation, or at least we didn't find any. And this one is when you up the number of cities and you up the scaling as well. So you put them in a larger area. And this one as well seems to go really up. We really wanted to see what's beyond, but it's very hard to compute. So as a remark, we used some heuristics on our 2-opt, which may be losing optimum. So this means that the results are actually underestimated. So the blue bars are actually maybe higher. So to finish quickly, as a result, we effectively modelized speed, acceleration, and inertia in the TSP. We had some insights and we had some complexity results. We showed that it's an NP-hard problem. And we proposed an algorithm using A-star Oracle. And we did some experimental results, which hopefully motivates the problem itself. So as a future work, you might want to try to find better algorithms, so approximation algorithms, or maybe show that the problem cannot be approximated, something like this, or some heuristics. And you might want to try to attack the NP hardness proof when visiting speed is not set to 0, because our proof does depend on this visiting speed being 0. Thank you very much.